Okay, we will continue now. The next speaker is Alex Jenkins, and he is the head of dairy at Communique. He has been in that position for the last 4 years, and he's specializing in mineral nutrition. And he has been in the industry for about 13 years. And there's no doubt that Alex is the industry expert on this presentation on lameness and minerals. So Alex, we're looking forward to your presentation, and welcome and thank you.
Thank you, Julian. Can you hear me all right?
I can hear you, and your presentation is also visible.
Great. Okay, fantastic. Thank you. That is what I was after. Cool. Now I decided to start my talk with my mute on, and then I realized nobody could hear me. All right. Well, thanks very much for asking me to come along. What I'm going to do today is give you a bit of an understanding around lameness, what causes it, what to do on farm, why we really care about lameness too much, and then give you some information on minerals as well. The mineral side can get very, very theoretical and quite maths heavy. So I'm going to leave all of that out and just keep it very practical. So jumping straight into it, lameness. Lameness is measured with the locomotion scoring of animals. Lameness is obviously damage to the animal's feet, and it's measured. Let me get the pointer here. Here we go. It's measured by looking at the animal standing and when they're walking. If she is standing with a flat back and walking with a flat back, we give her a score of 1. There's no milk loss on pasture and TMR. If she's mildly lame, she stands with a flat back, but when she walks, her back arches over and her head drops a little bit. This represents a small inflammation in the hoof of the animal, and there's a small milk loss on pasture and TMR. You'll see these numbers of milk loss is different for both of them, simply because pasture animals have to walk. They use their feet a lot more than TMR animals. A moderately lame animal is score 3. You'll hear me talk about score 3 cows. These are the ones that we really need to keep an eye out for, because she stands with an arched back and she walks with an arched back. And this animal is the one that we need to treat, because if we leave this animal, she is 4 times more likely to get worse than she is to get better. And if we look at her milk loss, especially on pastures, of 8%, it's almost the same as a cow that's limping with 11%. The difference between a 3 and a 4 is that a 4, you can tell which foot is lame, whereas with a 3, you can't. She's not limping in any one particular limb. She might be short stepping slightly, where the back feet don't actually overlap where the front feet are when she walks. A severely lame cow is usually limping very badly on the way to the slaughter truck. These are very, very sick cows and very difficult to get back. So I tend to call a score 3 as a lame cow, a score 4 as a tripod, and a 5 as a broken tripod. We need to identify all of our lame cows, our score 3 cows, and do something about it. Record them, treat them, so that we don't end up rebreeding chronic lame cows, etc., into our herds. Before we go anywhere, I just want to give you a quote by Mike Hutchins. Never use an additive when the same effect can be achieved by management change on the farm. And we see this so often. If we look at bottleneck theory, often the inputs that we put in from one side, if we're pushing inputs into the pipe in terms of effort and time and money, are hampered by big dents in the pipe that could be various things. Now, very often I will go on farm because I'm a mineral guy. People go, oh, we've got a selenium problem, selenium this, and everyone's going bossies about selenium. What I call that a gold-plated dent in the pipe, because everyone's focusing on it, but it's usually not the greatest dent in the pipe that we need to look after. If we sort out calf rearing just to the level where it's less than lameness, the impact on the business is less than lameness, then we can focus on lameness. And once we've sorted that out, then we can deal with the milk fevers. And once we've got all of that under control, then we can start focusing on selenium. It's a very easy thing to fix by just adding more selenium, but all of these other things take quite a lot more effort and focus on the farm. So always remember that don't just throw an additive at a problem. We always have to look at management first. The 5X rule of lameness, this comes from 47,000 cows that myself and my colleague Liz van Papendorp, or Liz Keen, she's now married, we've done 62 farm evaluations. This represents just under 10% of the national herd. If we're looking at a milk loss of 0, 1, 8, 11, and 34% for each of the different scored animals, our average occurrence of score 1s is about 50%, score 2s is 30, score 3 is 16% of all of these animals were a score 3 and a 4 and a 5, representing an average loss across all these 62 farms of almost R500,000. A farmer can identify a lame cow because they're limping. Score 4 cows and score 5 cows are limping, and it's fairly easy to spot a limping cow. So they see 3.4% of the lameness on their farms. But when you actually score them, these score 3 cows are actually also lame. So the farmers are only seeing 3.4% out of the 19.3%. So the 5X rule is for every tripod on a farm, there are 5 other lame cows that are losing you money. And this is actually corroborated by two papers that were written by Zinpro, and they found that farmers see between 10 and 23% of the lameness on their farms, and in South Africa this figure is just south of 15%. So where does this 470,000 Rand come from? If we have a cow that's lame, she's going to do less walking and she's going to walk more slowly. If she's walking less, she's going to spend less time near the feed, and she's going to slug feed when she gets there because she's hungry. Or she's going to lie down for longer, so then her eating bouts tend to be less frequent but much more aggressive. So she slug feeds, and she has a lower dry matter intake. By slug feeding, we go down the acidosis route. We create inflammation, we remove glucose, we'll get into that a little bit later. We produce poor keratin and they just get more lame. With low dry matter intake, we start affecting body condition score, and there's our fertility, our poor pasture use, milk drop. There's a whole cascade that goes on. With slow walking, they just take longer to get where they're going, so they stand for longer. That messes up their time budget, and the bad gets worse. So this is something that we really do need to care about. And if we look at lameness effect on reproduction, if we've got a normal days from calving to pregnancy of about 85, lameness will push that right out to 120. So it's the second most damaging thing to reproduction after a cesarean section, which is surprising and definitely something we need to focus on. So when we get down to the nitty-gritty of it, the lesions that are involved in lameness are divided into 2 types. We've got infectious lesions, which are a disease that is passed from cow to cow. And then we've got non-infectious lesions, which are mechanical damage of the hoof. So when we're dealing with infectious lesions, such as digital dermatitis, that's hairy heel wart, you may have heard of it, heel erosion, foot rot, etc. These are organisms that we need to deal with, and we deal with that by improving hygiene and sterility on the farm. So for infectious lesions, we use foot baths and we use hygiene scoring. If a cow is clean, if it's a score 1, nice and clean, or a score 4, very dirty, caked mud on the lower limb, obviously walking through a foot bath twice a day is going to have a much more positive effect on this animal than on this animal. And so we need to identify which lesion it is and react appropriately. For non-infectious lesions, we've got white lines. The most common ones are white lines. just remember where this lesion is on this foot, and I'll explain to you why it's there, specifically right there, a little bit later. Toe ulcers, when animals are just walking through their feet, they just wear their feet out. We see this a lot on pastures where the pedal bone actually pushes through the bottom of the claw. Sole hemorrhage is just this pink color on the bottom of the hemorrhage. Toe ulcers as well. Well, sole ulcers can be damaging, but toe ulcers is on the pastures. Corkscrew claw is a genetic thing. So these are non-infectious lesions. So a cow with white line disease is not going to give other cows white line disease. And what do we do with these? This is one of our flashcards. A foot bath won't fix this. You need to understand what lesions you're dealing with, because if you have, so there's a process in dealing with non-infectious lesions. We need to measure how bad the problem is. We need to analyze our lesions by speaking to our vet or the hoof trimmer or the farmer if he's good enough at trimming. And then we need to investigate what could be causing these mechanical damages. We need to a plan, we need to execute it, and we need to review. So this is a much more management-based process. There is some nutrition involved, but it's much more management-based for non-infectious lesions. The hoof is divided into different zones, and the ones we're going to talk about right now are zones 3 and 4 and 1 and 2. So around the edge of the hoof, this is the white line area, and 3 and 4, these are the critical areas that we're going to see. The classic question, I love asking this because the answer is always the same. And I have a little giggle to myself every time. I say, so farmer, what's causing lameness on your farm? And he says, no, it's the quarry that I've got. It's these little sharp quartz stones are getting into my feet, and there's nothing I can do. It's just the quarry that I've got. But what people don't remember is that a hoof is a castle that falls from within. It's factors within the hoof that are causing lameness. And the sharp stones that you're digging out of feet are just a result of the problem. They're not the cause of the problem. So let's start with a bit of anatomy. A cow stands in her feet, not on her feet. So there's 3 structures here that we need to look at. So we've got the hoof capsule, which is like a bucket on the outside of the hoof. We've got the pedal bone, which is attached to the cow very firmly by her leg. And then we've got the suspensory lamellae, which is a structure. I picture this as little strings suspending the pedal bone from the top of the hoof capsule, and it's all around the hoof. And you can see it just a bit more clearly in the schematic here. And what's really important is that the bottom of the pedal bone, you can see it here. The pedal bone is horizontal to the ground. That's what we need. That's a healthy foot, because then the weight of that cow is distributed across the whole base of that pedal bone. Remember, I said, remember where the white line ulcer was? It's always in zone 3 and 4. It's nearly always in zone 3. That's a good hoof. Our pedal bone is nice and horizontal to the ground. That's great. The hoof has got 2 structures where the horn grows out of, called the corium. So this corium here is like the little white moon-shaped structure at the base of your finger. That's your corium. That's where your nail grows from. It's also got a corium on the bottom of the hoof, so that the sole grows and the hoof capsule grows. And so it sort of extrudes itself off the end of the foot. That's how structure grows, about 5 millimeters a month. But the keratin and the structure of it is such that the back of the hoof is actually softer than the front of the hoof. And when this gets worn away, we end up with this long slipper-shaped foot. And when you place a 600-kilogram cow on this structure, what's going to happen? This is now going to become your new ground level, and the pedal bone inside is going to rotate. And this rotation of the pedal bone, this back section of it, increases the loading on zone 3 and 4 of the hoof. It works to grind away the soft structures inside the foot, and it produces blood in the keratin, and the soft keratin that is then produced on the white line allows stones to access that hoof. And here's some actual bones from the Hoofschmidt. These are heifer pedal bones. It is a top view of the bones, but they're nice, they're smooth, they're as bones should be. This animal is in her second lactation, only 2 lactations later, and she's already got calcification on the underside of her pedal bones. So now that is what she's walking on all the time. So if we talk about the irritation of having a stone in your shoe, this is what she's dealing with by a second lactation. And then he had one from a 5th lactation animal, which I don't even think this animal was capable of walking any longer. So we're not talking about the little stones getting into the foot. It's the reaction to this increased pressure on the pedal bones that is causing calcification of the bone, which mashes up the tissues inside the foot, producing this soft keratin. So if we look at a white line, for those of you who haven't lifted a cow's foot, the sole and the capsule are joined together by this white line structure here. And when we get this damage inside the foot, there's hemorrhage and there's bleeding, and you can actually see it. This is a shaving. I spent some time with some hoof trimmers, working with them and understanding this stuff. And this is a shaving off a cow's hoof, and that's the outer wall. And there's the white line, and you can actually see the blood caught in the white line of that shaving. And essentially what it does is it turns a very hard cheese into a very soft cheese. It just makes a structure that should be very dense and very hard. It puts a whole bunch of holes in it. And what are the holes filled with from a microbial point of view? They're filled with food. They're filled with blood. And so you do get a lot of infection in the foot, but they are not infectious lesions. One won't give another cow a white line disease. But this is the main problem, was the trauma within that causes white line diseases. So what's going on with our score 3 cows? We've got 2 examples. I was on a farm and I just separated out this cow who's standing, has got a very clear arch on her back, and this cow who's got a tiny little hump on her back. I just wanted to see what was going on with this cow. I knew that this cow had a problem, but she wasn't limping. Bear in mind, and let me repeat that, this white animal was not limping. This is what their feet looked like. That is the white line lesion on that cow. And unless you are checking her with her curved back, you would never know that this cow has got a foot problem, because she's not limping. This white cow has got 2 tiny little white line lesions starting, just cracking. Can you see the white line coming down here? And so with this cow, it took 3 passes with a hoof knife, and we had trimmed those cracks out, and she was absolutely fine, good to go. With this cow, we ended up, you have to chase this, because what happens is the crack starts, and the pressure of the cow walking on the manure and the mud, it pushes stuff up in there. It's like getting a splinter under your fingernail and then packing more splinters in behind it. It's extremely painful. And this cow, so with this, to get rid of the infection, you've got to open it all up to the air. And we ended up trimming almost the whole side wall of this cow's hoof. It was almost a surgical trim that she needed, and she wasn't limping yet. So this is why lameness and spotting those 3 score cows is important. So how does a cow get to that situation? It's all about balance. Here's that cow's foot again. If we look at the outer claw versus the inner claw, the outer claw is a lot bigger than the inner claw, and it's not a genetic thing. You know, the genetics of a cow's foot, the outer claw might be marginally bigger, but certainly not this much bigger. So how have we gotten to this situation where the outer claw, literally while she's walking, she's only walking on one claw here because the other one's not even touching the ground? So how do we get to that situation? It's all about the walking motion. So down here, this is now my schematics. You must apologize to Richard. We're all using the same poor level of art today. The grooves on the concrete must always run in the direction of travel. They must never run across the way the cows walk. And it's for the reason that the walking motion requires the outer claw to catch on the edge of a groove. So if these grooves are rounded off, the cows will still start slipping. That's why these grooves need to be fresh. They need to be able to catch that outer claw. And when a cow lifts her foot and moves her foot, she does so in this sort of oval motion, this where as she places her foot down, the inner claw slides on the ground, provides some restriction, and the outer claw actually catches it. Now, what happens is the outer claw, this is a much more gentle movement, and it's a wearing movement. It wears out the inner claw, but the outer claw is bearing the impact, and so the foot responds by depositing keratin onto that outer claw. And if you're not balance trimming your cows, if the farmer does not trim their cows once a year, that outer claw can get bigger and bigger and bigger while the inner claw wears away, and eventually she just ends up walking on one claw. So that's the thing about balance. It's widely recognized that heat and summer are the absolute worst times for lameness, especially at the end of summer. So let me just start that. There we go. And it's because of heat stress and various stresses inside the animal. A dairy cow produces as much heat as 160-watt light bulbs just from fermentation and the fact that she is a ruminant. So heat stress is a major challenge, and this is a transition across from lameness into the minerals, because what we need to do is mitigate stress in our animals, be it heat, be it any kind of stress. We need to reduce that. If we look at the effect of stress, we have a gut, and not to preach to the choir too much, but it's made up of an epithelium of these microvilli on top of these epithelial cells. What holds these epithelial cells together are these tight junction proteins. So you have a paracellular space between the cells here, but what's stitching them together and keeping the gut contents out of the blood are these tight junction cells. And there's a whole bunch of them. They're proteins that sort of upholster the two cells together. Now, being proteins, they're made up of amino acids in a chain. Now, a chain of amino acids is a very stable structure. It's not going to change very much. When the protein is built, it starts folding, and in its folded structure, it's very stable as well. So the claudin and occludin that make up the tight junction, that it's a very stable structure, and that's great. But under heat stress, the folding structure of these tight junction proteins starts giving way, and that whole thing is zinc dependent. And that folding and the stability of that is zinc dependent. So here's some more of my brilliant art. So here's two epidermal cells in the gut. Here's the brown gut contents, because we know what a gut contains. And here's the green safe cow's bloodstream with the tight junctions holding those two together. If those tight junction structure starts relaxing, the gut content is able to get into the blood. And what happens when you get a cut and you get an external infection in that cut? You get a massive immune response. And so what we essentially have during heat stress and during any form of stress, and they've even proved this for psychological stress, that the gut responds and these tight junction proteins start relaxing. You get this huge immune response on the biggest organ in the body. And so you get this massive requirement for energy to fuel the immune system. And that energy comes in the form of glucose. And Lance Baumgart in the States is doing all the seminal work on this. And his latest measurement is 1 kilo of glucose every 12 hours. So in the heat, in the hot times, that represents 2 kilos of glucose a day. It's the equivalent of about 3 kgs of maize that just goes to gut inflammation and stress. This is the concept of leaky gut, and is a big focus for the animal science industry on a global basis at the moment. So managing stress, we need to cool those cows down. Kenneth showed us the difference between cooled cows and hot cows from a milk production point of view. That the milk production drop is because all the glucose is going to the gut, not the milk. And so heat abatement in the holding yards. On pasture farms, it's quite difficult to do heat abatement because the cows are out in the sun all day. But we can achieve 65% of the heat abatement that we require in the holding yard, where the cows are all packed closely together. The radiant heat between them is enormous. So cooling them down, putting them in shade, putting fans over our holding yards, reducing mud and shaping the roads, having a summer mineral concept is really, really important as well. And time budget, making sure that those cows are in front of food and not standing, wasting time out in the sun. Which brings us to minerals. I'm not going to talk too much about this slide because I'll just read it to you. You can read it to yourself. But let's just understand that trace minerals are massively important. They are as important to nutrition as the spark from a spark plug is to a Formula One car. If you don't have them, everything goes wrong. Nothing works properly if your minerals are unbalanced. And so I was going to get into the real nitty gritty of how much is required, et cetera, but it's such a dynamic field on a farm, and there's so much involved that with the nutritionist and the vet and the farmer and the consultant, we work together and we design a mineral program, or we design a mineral premix that the farms will use. So what I wanted to give you now was just some overview of why each of the trace minerals is important and why we care about it. And then we can, I'll show you what to do as a vet to actually manage it. So zinc sparks is actually a really interesting thing. Sorry, I'm just trying to figure out how to use my, here we go. Okay, so zinc sparks, this was it's a TED talk that was done in humans. And it's a guy that is trying to work on in vitro fertilization of couples, because people who go for IVF generally want a child and end up having 2 or 3 children. And that can be a real economic challenge for people who just want 1 child. And so what he was trying to do was determine at the point of fertilization, what is going on with the minerals. So he actually, there's a couple of videos. The first video shows the egg with the spermatozoa just underneath the, just inside the egg. And he's tagged all of the zinc in pink in this slide. And what you will see at the moment of fertilization, the cell pulls in a huge amount of zinc, uses it for that moment of fertilization, then kicks it out again. And they can measure the radiance coming out of the cell by, you can see there's the pink, the zinc is in the cell, and then it gets all kicked out again. And that cell is now fertilized. And based on the intensity of the flash that they can read, you can actually tell, so there's 9 in a tray. Based on the intensity of the flash, you can actually say that this is now a blastocyst, this is a blastocyst, those 2 didn't do anything, they're unactivated, and the other 5 are not viable. So now out of those 9 cells, where before we didn't really know whether they had taken or not, we can now select 2 and move forward. So zinc is absolutely critical everywhere. It's the first trace mineral we look at, and quite frankly, it's like that for a reason. It's used in over 3,000 enzyme pathways. Zinc is everywhere. So getting your zinc levels correct is really important, especially around fertility, which brings us to manganese, which is the pink mineral. When you think fertility, think manganese. Because in the corpus luteum, which obviously, as you know, controls early hormonal development, etc., of the pregnancy, there is 11 times more manganese than there is selenium. So everybody feeds lots of selenium for fertility, but we really do need to be having increased levels of manganese and good quality manganese from good sources for improvement of fertility. Copper. This is I was looking for a picture of the straw that broke the camel's back, so I like that. Copper is unique amongst the minerals in that it is taken up from the gut, it's transported to the liver, and there it builds its house. It doesn't really leave. It doesn't really get cycled through like the other minerals do. So what you tend to get if we overfeed copper in a situation, you will get liver copper levels rising and rising and rising and rising over, this can be over the entire replacement heifer's rearing time of 2 years. And when they get into milk and their copper levels are too high in the liver, it gets to a critical point. And that critical point is not well understood. I've seen animals that are absolutely fine at 950 on the copper scale, and they're fine. I've seen other animals have a copper toxicosis at 350. So we use 450 as a really good trigger to do something dramatic, because what happens is copper builds and builds and builds in the liver, and then there is a mechanism in the liver that just says enough is enough. I'm saving the cow and I'm getting rid of this copper, and it dumps all of the copper into the blood. The copper binds with the with hemoglobin, reduces the oxygen carrying capacity of blood, and that's when you get animals dying from copper poisoning. Copper poisoning is not, it can be an acute thing where the animals have just eaten something that's extremely high in copper, but it is more often than not a chronic problem of oversupply of copper for a long period of time. And copper management is something really, really critical that we need to look at in dairy farms. Cobalt is required for fiber digestion. Oh, my picture's gone. Sorry. There was a large diagram of a B12 molecule here. It's a very big, complicated molecule, and it centers around cobalt. And yeah, it's important for the binding of bacteria to the fiber source. And so, as many of our cows are on pasture and all of our cows feed on fiber, that's really important that we have cobalt correct. Selenium is all about the site of action. Selenium is a big one, and if you want to polarize a room, talk about selenium. So I've only got 2 slides, and I firmly believe that everyone's entitled to my opinion, so you can take it or leave it as you wish. There are 2 forms of selenium. There's sodium selenite and selenium methionine. This is what's in. It's cheap. It's in every single premix. It's the form of selenium that is most easily available. Selenium methionine is organic, and it's fancy and expensive, and it's new tech and all the rest of it. We need to understand what we want out of selenium supplementation. What we want out of selenium most of the time is the antioxidant capacity of selenium, which improves our antioxidant ability and reduces free radicals, etc. And that is glutathione peroxidase activity. Sodium selenite is hugely effective at going to selenocysteine and moving to glutathione peroxidase. If we want antioxidant ability in the animal, we can get that very easily and very cheaply from sodium selenite. Selenium methionine, on the other hand, is a storage molecule. And I'm not bashing selenium methionine at all, because I sell selenium methionine. So it's important for us to just understand where these things are used. There's a feed company that produces that uses selenium methionine to produce high selenium eggs, so that people that eat the eggs can get a supplementary source of selenium. That's a fantastic way of doing it. Selenium methionine is stored in muscle, milk, and eggs. I've left eggs out because dairy cows don't make eggs. But if we were to look at the life cycle of a dairy cow, during lactation, most of the time during lactation, we're chasing this antioxidant ability. We want our animals to be as healthy as possible. We are not getting paid for high selenium milk, and we have a storage pool in the muscles. And So when would we want to store a lot of selenium in a dairy cow? During the dry period, because the dry period is when she is close to calving, and storing selenium in the muscles, in the fetus, and in the colostrum is exactly where we want it. So pushing selenomethionine in the dry period only benefits the calf all the way. It also benefits the cow because she can have a store of selenium to use during her fresh period. So if we're looking at selenium to dry cows, we increase the selenium status of the cow. Fetal selenium levels are 2 to 4 times greater than maternal selenium levels because the fetus actually changes how the cow takes selenium out of the diet. We get selenium content in the colostrum, and we increase the IgG absorption and the glutathione peroxidase content of the calf. And this is what's important. So if we are to spend money anywhere, let's spend money on our dry cows and our transition cows, that early days. If we really want to chase additional benefits, then feeding organic selenium to high producing dairy cows is definitely a good thing. It's not a waste of money, but not every animal on the farm needs organic selenium. So let me just finish with that comment. Chromium is the next big thing. Chromium makes the cow more insulin sensitive. It's a really, really interesting mechanism that chromium has. It's super simple. And do you remember the amount of glucose we use during heat stress, a kg of glucose every 12 hours? Well, this uses glucose much more efficiently. It makes the cells utilize and take in glucose, and so improves immune function, dry matter intake, condition fertility. It's incredible what chromium is doing. And we're looking on TMRs, 8 milligrams, so 8,000ths of a gram of chromium is on the 9 trials that Zinpro have done, is producing 2.5 liter milk response because of improved dry matter intake and improved immune function and body condition, etc. So it's a big deal. So now we come across to managing minerals. Actually, as a vet, how would you be involved in this whole process? We've got to pick the correct tissue to sample, first things first. So if we've got an engine and a fuel tank, where would you measure fuel in your car? Do you measure it with a sensor in the fuel tank, or do you measure it with a sensor in the pipe right before the engine? The obvious answer is in the fuel tank, because if you're measuring it in the pipe, the moment your fuel gauge, it will always be full, and then it will be empty and you will stand by the side of the road. So the same thing with picking the correct tissue to sample. We've got blood, iron, and selenium, iodine, iron, and selenium from the blood, and zinc, copper, and manganese from the liver. Those are the tissues that we should be looking at to analyze our minerals. Now, liver biopsies we'll get into it now, but they're challenging to do, much more so than blood. So let's understand the difference. If we've got a normal distribution or a homeostatic distribution, right? Under normal circumstances, if we're looking at selenium in the blood, as selenium intake improves, you're going to get a commensurate rise in selenium levels in the blood. If we look at zinc, copper, and manganese, they're homeostatically controlled, which means, like with copper, now let's use zinc. Zinc is taken in, it's taken to the liver, and it's stored there. The levels in the blood are going to rise to a point, and then they're going to remain constant. And all that's going to change is the amount of zinc in the liver is going to improve. When there is a requirement for zinc, it's going to draw out of the liver, pump it back into the blood, and that's that homeostatic mechanism. It uses the liver as the fuel tank, right? So if we're trying to make a decision at a herd level of whether to improve zinc supplementation or increase manganese, and we're looking at blood, blood is not necessarily useless as a mechanism or as a tissue. If the animals have got incredibly low manganese, it means that we're running out of fuel in the pipe right before the engine, and that's a problem. If they've got incredibly high manganese in the blood, it means they've actually overwhelmed the homeostatic mechanism of the liver, and now we actually have a manganese toxicity problem, which is very rare. But that's why we need to just decide on which tissue to use. If we are collecting liver biopsies or targeting any minerals, it's really important to look at these two cows and decide which one is the optimum cow for our herd, because that's the one that we want to target. We don't want to make decisions for 1,000 animals that look like this based on the liver of this cow after we've just killed her. She has clearly got an enormous immune challenge. She's had surgery. She's in a bad way. Her liver content of minerals is going to be very, very low and very poor and not indicative of the rest of the animals that we're choosing to lactate. So we want 20 cows or 10% of the herd. 20 cows is usually what makes people's eyes water. So 10% of the 1,000 cow herd is never going to happen. They need to be healthy. If we want to assess the herd, we want them around peak. If we suspect problems, we can move those days in milk sooner. We need to record cow number, production, and days in milk. And here's why. If we look at liver copper, say we say that 100 ppm is adequate. But if we actually look at pre-calving, the dam will be slightly higher. Post-calving, she's given a whole bunch of her minerals to her calf. It carries on, she rebuilds those levels right up. If we take an animal at calving and we measure her copper levels at, what's this, 80 odd, 85, 80. And we say, no, we need to be at 100. We need to improve copper supplementation. So we put extra copper in the diet. But then naturally she starts absorbing more copper. What are we going to do to her over here? It's going to push right through the roof. Similarly, if we take the same cow in late lactation and we measure her copper levels at 120 and we pull all the copper out the diet because she's too high, we make poor decisions. And this is why cow records are so important. And this is an example of what a liver biopsy looks like. I just want to give you an idea of data versus information. Surieta did a really great job of converting a whole mountain of data yesterday into quite usable information. And this is what we're trying to do with the minerals. There's a difference between doing mineral nutrition and doing grade 3 maths. If we have our range here of 125 to 250 and we have a bunch of zincs, would you say that in general this farm is deficient or okay? I would say it's probably deficient. If we're looking at there's 119, there's 110, there's 111, there's a 98, there's 123. All of those are below the lower level of zinc. So then we look at this and we go, oh dear, we need to add zinc. But if we compare our mineral levels to a database of samples, we see that 70% of those normal cows fall below the level of 125, but above the level of 75. So is this farm deficient if we make this bottom number 75? And this is why straight mathematics like this, it doesn't really work, because Robert Pulse, this is from 1980, but this was really helpful, useful information. A deficient cow is less than 60 to 120, marginal is 75 to 120, adequate is 75 to 300, and high is 900. Can you see the inherent problem with trying to use straight maths when we're dealing with minerals? If I've got a cow that's sitting on 100 or 110, is she deficient, marginal, or adequate? If I've got a cow that's sitting on 500, where does she fall? Is it toxic? Because 360 is toxic to 1500. So this is it's important to be very practical with minerals. And then come the antagonists. The Joker is always the antagonist to Batman. He doesn't sit back and just go, oh, well, you know, Batman, I wish him poorly and do nothing about it. The antagonist sets out to ruin the day. And minerals do not play well with one another. We've all seen this graph, and you can see that high iron antagonizes zinc and manganese and copper. And Also, zinc antagonizes calcium uptake, etc. The antagonisms between minerals are really important to understand. They're very difficult to measure. So where do we start? We start by understanding the two main ones. Iron, zinc, manganese, and copper. That's the kite of doom, and the fiery triangle is copper, sulfur, and molybdenum, forming a molecule called thiomolybdate. They do this in the rumen, in the gut, in the liver, in the cells, and in the blood. Thiomolybdates can form, and they stop the uptake of copper. So let's see a real-world example of how this might actually play out. So here's a water sample that I did. 571% more iron than there should be in the water, 630% more manganese, and 3 times the amount of molybdenum. You remember, what are we looking at? We're looking at molybdenum affecting copper uptake. Do you think copper is going to be affected by the molybdenum in this water? Probably. And with this much iron and this much manganese, do you think that zinc and copper are likely to be affected? What's interesting is that this manganese actually stops manganese uptake, because this is manganese oxide and it's not available to the animal. So the manganese that we put in the feed is actually being blocked by the manganese in the water. So when we get a situation like this, we have got to work around the antagonisms. You've got to find a way to get them into the cow without falling foul of these antagonisms. So you get treated to some more word art. This is a rundown of pretty much every way that a mineral can go wrong. So here's a rumen, here's the acid stomach, and here's 2 epithelial cells in the lower gut. When we're talking about organic minerals, an organic is a chelate, is when you bind a mineral to a ligand, which is a molecule that has a carbon in it. So chelates, all of them bypass the rumen. By chelating minerals, we make that mineral unavailable to the microbial population, which is a 150 kilogram organism that wants minerals. And that bypasses the rumen. So we're already delivering more mineral past the rumen to the cow. In the acid stomach, the acid can break the bond. So we now have free mineral and free ligand floating around in the system. This can just get washed out the end of the hose pipe and not touch sides, which an alarming amount does. It can get bound to antagonists like phytate and toxin binders, etc. in the diet. So that's the first sort of 3 fates of an organic mineral that can get broken up by the acid stomach. If it makes it through the acid stomach, now we've got to look at the quality of the binding to that mineral. It's either bound too loosely and it fails early and it gets washed out, or it binds too tightly, like in the case of EDTA. If somebody swallows a bunch of mercury, they get rushed to the trauma ward and they get drenched with EDTA, which soaks up all of the minerals in their gut and all comes out the back end. All the heavy metals, everything in their gut gets bound by EDTA, and then they go on a course of mineral supplementation to get it back. So say our mineral has now arrived at the small intestine, the site of absorption. This is where we start looking at our transporters down here. A zip transporter, this is a normal mineral transporter, and the amino acids are obviously for proteins. This is where our zip transporter comes into play. This is iron around the transporter, and this is zinc trying to get into that transporter. It's just outcompeted. There's too much iron there, and this is in a constant flow, a river of digester passing this receptor, so it just gets washed out. What we need is and with amino acid complexed ones, it goes through the amino acid route into the cell. It can be stored, or it gets transported into the body and moved onwards from there. So how to manage minerals? If we're looking at a standard sort of two lactation curves, if we're looking, this is just a pasture situation, it's different for TMRs, but this is a very hot period. This is a very cool period. If I visit a farm during June or July, I'm going to start looking at the spring flush and making a plan for summer. We're going to change the minerals based on the amount of inflammation, the farm goals, the targets, etc. that they're using. At the end of summer, kind of January, February, March time, or April, we'll go back to the farm and we'll say, okay, we had a whole bunch of goals. How did we do? We wanted to do some things. What did we actually achieve? And we'll review our summer strategy that we developed in winter, and we'll come up with a winter strategy. What does our silage look like? Do we need to worry about toxin binders? Do we need to worry about gut health or chromium or milk production or fertility? What are we doing for that period? So this sort of biannual consultancy around minerals is it's a nice cadence to do it. It's a nice way to do it. And in this, we will get the nutritionist and the vet and the farmer and ourselves and anyone else that's involved in the feeding of the animals to come up with the plans. Setting some goals for the coming season. You know, by setting goals, it's like pulling an elastic band. If you pull the front, you're going to put pressure on the back of the elastic band, and things get pulled forward by setting goals. We need our goals to be measurable and achievable and realistic, and this is a big part of what we do, is trying to identify what we can do on farms. So in summary, if we stick with the analogy of a dairy cow being, you know, the metabolic equivalent of a Formula One car, you've got to ask yourself, which team would you choose? You know, the team that knows what they're about, that knows their roles, that's highly specific and extremely trained and competent, or would you like the rustig op die plaas team that's just going to fix problems as and when they arise? So thank you very much. That's my story.
Thank you, Alex.
Thank you.
Do we have any questions? There's one student that asked whether you know of any place that one can go for hoof trimming courses that you will recommend.
I don't know of anywhere that actually does formal courses, but contact with the Dairy Smith. I'll put Gert's details on the chat. Give Gert a call and ask him and find out. Well, I'll give him a call and ask him, and then if he doesn't have a resource, I'll put his details on the chat.
Okay, it's Gert van Zyl.
Yes.
Yeah, that's correct. Okay. Anyone else would like to pose a question to Alex?
Thank you very much, Ilse.
You've got a thank you here, saying it was very informative.
Great, thank you.
Let's just wait a bit.
Yeah, minerals are a challenging thing, because lots of times the feed companies are, rightly so, they're focused on things that are.
You muted, Alex.
Am I? Is that better? Can you hear me now?
No, I can't hear you. Okay, but Dr. van der Leek, he has a question.
Yes, Alex, yesterday we discussed the conflict of interest and bias when you're dealing with commercial companies. How does Communique handle that dilemma?
Can you hear me now?
I can hear you.
I can.
Okay, great, fantastic. Yes, the answer is very delicately. We are involved in managing sort of mineral strategies for a lot of people, and it is absolutely critical to maintain your integrity at all times. It's all about trust. The moment the market stops trusting you, you've lost the game entirely. So yes, never share anybody's information. Keep everything as siloed and separate as possible, and just add as much value. That's a lot of what I do, is I try and find the difficulties in the industry, what a guy's battling with. It's why I set up that liver curve, because a lot of nutritionists will look at it and they just go, I'm not really too sure. So we do that sort of tissue interpretation. We do water analysis. We do various other things, hoof scoring and visiting people on farms. So we work together with the industry very closely. And yeah, but how to manage the conflict of interest, each dairy, each company has got their own strategy, and we fall into that strategy and advise them accordingly to the best of our abilities.
So, Alex, can you just tell us a little bit about the international footprint? So, relationships with Zinpro and others. And
yes, yeah, thank you. Yeah, so we've got the minerals that we deal in are from Zinpro. Zinpro is the original research and supply company for organic minerals. They've got a huge amount of data and more than 350 peer-reviewed papers on minerals alone. So they have an enormous raft of information, which is great. We also work with Villafos out of Europe and with Arm & Hammer out of Canada, bringing in products for calcium management around calving and calf diarrhea products, etc. But Communique, absolute cornerstone of Communique is the science behind every recommendation we do. It's never our opinion. It's the proper science that we need to recommend. Thank you.
Thanks so much, Alex.
Cheers. Thank you so much.